Polytechnic Institute and the Military University of Colombia. Our agenda for today is going to start with the motivation for our development, then a briefly explanation of balance system and motor recovery procedures are going to be taken to then go to the 2-degree of robotic platform mechanisms and all the consideration of the kinematics and dynamics modeling. Also, we're going to present the performance and how we assess the performance of these mechanisms to finally finish our presentation with our conclusions. First, according to the World Health Organization, more than 1 billion people, around 50% of the world's population, have some disability. From them, between 100 and 200 million adults have function difficulties, where cardiovascular diseases is one of the leading causes of death and disability in the world's adult population. Where stroke, as part of the CVD condition, is the second cause of death and the second cause of more years lived in disability. Moreover, 50 million strokes per year worldwide occur, and 50 million die, and 50 million are disabled or kept disabled for life. Then, on the other hand, we have the balance system. Balance is achieved and maintained by a complex set of sensory motor control system, working in a file like the sensory input stated by the vestibular, visual, or proprioceptive system, where signals are integrated by the cerebellum, cerebral cortex, or brainstem, basically, to conduct the impulse to actuators that in this case will act as the motor input and performed by the motor system. Then we get the balance in our case. Then any issue on area affectation of all those systems will cause impairment or disability in the human being, especially in a stroke where cerebral cortex is mainly affected. It affects the motor system. Then we can find people with several disabilities, especially related to balance, and then have to start a motor recovery process to go from the stillness to the complete rehabilitation, let's say. Then the objective of motor rehabilitation is to restore function and prevent further disability. We usually can classify the rehabilitation into 3 stages. First, the basic movements, where the patient gradually leaves the state of stillness. Second, assisted training, which is normally executed in a specialty center, rehabilitation center, and performed by trained medical personnel to get this task. And the third stage is the improvement stage, where the patient continues their therapies outside of the, let's say, the hospital facilities with a periodic orientation of the specialists. In this case, assisted training is usually the field where we as researchers and engineers apply and develop the novel technologies to enhance and promote various rehabilitation procedures. Ultimately, robotic assisted therapy has become more used trend in this kind of procedures, because robotic, in fact, ensures repetitiveness, accuracy, and overall do not get tired. So we can assure the same movement, the same procedure all the time. But it's hard to be reachable with human or traditional therapy. It's important to, as we identify that the balance is the more prevalent function affected by stroke and by disability in general, we decide to develop a 2 degrees of freedom robotic platform mechanism. We found that at least 2 degrees of freedom were necessary to achieve most of the movements necessary to perform balance rehabilitation tasks. For this, our platform consists in two mechanisms of fall bar, which are highlighted in blue and red here in our diagram, where the unions between the links A, B, and C, B and C are by spherical joints. This in order to avoid constraints in a small translational movement that our platform could have presented. And these two mechanisms are linked by a universal joint set on the origin marked as O0, just in the middle. That's also the origin of our coordinate system and a reference system to take into account into the kinematic and dynamic modeling. To the kinematic modeling, we use an algebraic approach where we use like this method to facilitate the mathematical modeling and analyzing. We place both mechanisms orthogonally to avoid that the movement from one mechanism affects the movement of the other. Then we could make a separate analysis of the kinematics of each mechanism. Then to this, we basically start by placing 2 points, P2 and P1, and then we create a two equation system with two unknowns, which in this case will be the output angle called beta and alpha. Here we show the calculation of alpha, and the same process is going to be replicated in the beta angle calculation. As our platform is not going to work alone, that means going to interact directly with the human body, we consider that the kinematics of the human body is an essential part of our project. In fact, the center of mass of the human being is considered of the end effector of our system. So all the paths and movement that we're going to perform are going to be referring to the end effector of the center of mass of the human. In this case, to simplify the modeling, we consider the human as a solid bar of 2 degrees of freedom located at the base of the platform, where the output angles alpha and beta becomes the input angles of these 2 degrees of freedom, let's say, serial manipulator, where LC is taking us the distance to the center of mass of the body. Then, to assess the torque requirements and to implement the control models to perform their desired rehabilitation movements, we calculate the dynamics of our system using the equation of motion product of the inverse dynamic analysis. To this, we take advantage of the Lagrange formulation, where we state that total Lagrange formulation as the sum of the Lagrange of the human plus the Lagrange of the platform. The Lagrange formulation for the platform considers only the rotational kinetic energy, because as we are assessing our dynamics in the central and the region of the reference system, we're not going to experience translation of the platform effect, and also we are not going to experience any potential energy from this platform. On the other hand, the Lagrange formulation for the human considers translational and rotational kinetic energies, and also the potential energy. As noted before, potential energy varies according to the position of the end effector, that means the center of mass of the human being. Then, to get the equation of motion of our system, we use the partial derivative of the Lagrange function, and then to introduce our matrices of inertia, coriolis, and gravity to our control blocks, we arrange all the matrices according to the speed, position, and acceleration variables. Then, to evaluate the performance and behavior of our system, we developed a PD controller with gravity compensation. This developed was placed on using Simulate from a lab, and the physics simulation of our system were implemented on C-Mechanics toolbox from a lab as well. Here, the control law is stated by the gravity and proportional gravity constants multiplied by the error of position and the error of velocity respectively, to then equalize our equation motion to our control law in order to get the general model of our control system. To evaluate or assess the performance of our system, we establish or set some values to our parameters for our mechanism, which can be seen here in the left side of our slide. And then we evaluate the trajectory achieved with the PD with gravity compensation of the platform with respect to a desired path. In this case, we did a desired path of that it's let's say a ellipse, in which we can, as we design a subabortive weights controller, we can see the oscillation through the trajectory until the system reaches the steady state. To evaluate properly to assess properly the performance of the controller, we use the mean squared error and the mean squared error, which present a root mean squared error about 0.5 centimeters along of the whole trajectory, and the whole trajectory was performed for 1 minute. Of now, this system is part of a bigger system called the System for Rehabilitation, for Balance Rehabilitation, which integrates virtual reality, psychological signals, skin glass electrocardiographical, skin conduction response, and breathing frequency, also as biomechanical signal as plantar and center operation. We believe that the integration of novel technologies such as robotics and virtual reality helps to enhance and improve the process rehabilitation outcomes, and also enhance the adherence to this process that has been found as a big issue in this kind of procedures.
Okay, you have 1 minute left. Osvaldo, I cannot hear you. Hi, can you hear me? Hello? Hello? I think we lost
Yes, we lost.
Osvaldo.
We will continue with.
Yeah, indeed, he was just at the conclusions. So I think if there is a quick question, we can address to him through the chat, hoping he will get back. I see his slides, so I guess he's somehow trying to connect again, but the mic is off. Martin, can you check why the microphone is off? Oh, now it's on.
It's okay.
Osvaldo, can you hear us?
Yes.
Okay,
Hear me?
so the paper is now open for discussion. Thank you very much for your nice presentation.
Thank you.
Is there any question from the audience? If not, I have one. Can you comment on, I saw some commercial devices which are doing some similar rehabilitation task. Can you highlight the advantages and drawbacks of your device as compared with the commercial products?
Sure. Okay, first of all, as we came from a country that most of the physical rehabilitation therapy is performed by hand, let's say that, and in our country we don't use too much robotic assisted therapy. Then the access to these platforms on systems is limited for our users. Our solution differs from other solution. Essentially, we can, because we design let's say a multitask platform that can be how to say adequate to several tasks. For instance, we develop and build our platform to perform with torque control that will have allow us to implement impedance controls or force controls. With that, we believe that we can make more adaptive the rehabilitation to the patient's necessities. And also, as we developed this system by the beginning, we believe that the cost of our development can be competitive compared to the current alternative in the market. Normally, alternatives in the market are aimed to recover gait, not balance. But we found that balance is the first step to be, or the first ability to, or the skill to be rehabilitated before starting to walk again, for instance.
Thank you, Osvaldo, for your nice presentation. And now let's move on to the next speaker, and with John Rodriguez Torres. And he is going to present exoskeleton glove with cable-driven fingers actuated by a differential mechanism. So, John Rodriguez, the floor is yours.
Hello, give me a moment.
Yes, please.
So I try to fix my presentation.
Perfect. We still don't see your screen. John?
Yes, it's 1 second.
Okay, okay.
Have to Windows, so I try to fix. Okay. Okay. Okay.
If
Can
you,
you? Yeah. Okay.
yes, now I
Can you
see
see?
your screen. Yes,
Yeah.
please
Okay.
go ahead.
So, good afternoon, everybody. My name is John Rodriguez. I'm PhD student in the Robotic and Mechatronic System program at the Instituto Politécnico Nacional. And today, in this presentation, the following topics are cover the introduction, the system consideration, mechanical structure design, the mathematical model, the results, and conclusion. Okay. So, the project is focused on helping people with muscular disease in the hands, which prevents the performance of grasping activities. So, and the hands are used to hold objects in the environment and interact with it. People who have joint and muscle damage often perform rehabilitation exercises that focus on daily work type movements, specifically grasping tasks through flexion and extension movements and manipulation tasks. Currently, there are different mechanisms and actors which are tools used by patients with hand disabilities in their daily life. So, for example, the exoglove PN, their left figure, and the EMG controls of robotic, the right picture. The exoglove PN, which use a pneumatic actuator, and the EMG controls of robotic glove, which uses a hydraulic actuator to facilitate gripping activities. In the mechanisms proposed in the article system, we use a ball and cable to support flexion and extension function by a cable-driven mechanism. Okay, to create a system as simple as possible, this project uses cable-driven mechanism in the index and middle fingers and the thumb. We can see. Let me. Okay, and the thumb is an abduction position to generate an opposition with other fingers. Okay, and instead for having a big system that requires one actuator or for each finger, like the show in the figure. In this case, the actor is here, right here. So this mechanism in the state of art take two motors for one and index and middle finger. The project is focused on supporting the flexion and extension to perform a natural movement. For the development of this work, the tendon extensor or tendon flexor are important because the investigation seeks to emulate the tendon movement use a glove. So, and the cable-driven mechanism is a flexible system that allows a natural movement and distribute force, otherwise the grip will fail. Okay. So the cable-driven mechanism provides greater lightness and facility in the assembly on a glove. To control the system, a configuration was proposed as shown in the figure. First, the graphic interface generates the path that the finger must follow. So this path is sent to control module who sends the position signal to the actuator to move the cable-driven mechanism and the current position of the actuator right here Um, the current position of the actor is compared to desired trajectory to minimize the position error. So, unlike the device where the fingers adapt to the surface and use actuator for each finger, this will propose the use of a single actuator using a differential mechanism for multiple fingers as shown in the figure. This mechanism provides the adaptive gripping movement with a single motor consists in the distribution of the force on the bowring cable, depending on the finger that requires more support during flexion. So the bowring cable is placed in small tubes, like here, here, and here. But in this figure, we can see the bowring cable with the tubes, like this one, this one, this one. So we can see the bowring cable is placed and attached to the surface of the glove to allow it to slip through. Then, without any restriction, allow the path the cable goes through the one finger to then passes through the other finger and finally returns. In this system, the motor generates a rotational movement and the user feels a longitudinal movement due to the cable. So to regulate this movement, there is a mechanism which is shown in the left figure, this one, that controls the total length of the cable of the bowring cable. So the mechanism has the function to release and wind the bowring cable, which is rolled up in the spool element 4, blue, this one. So, and its initial end is tied in the whole tree, right here. Then passes in the middle of the idler and feeder green object, which are in charge of tensioning the cable. There is a transmission radio, right, just right there, of 1 to 1.2 of the gears that move the feeder, the green object, and spool, the 4 object. Consequently to these gears, the feeder turns a higher speed and pulls the cable while unwinding from the spool. There are 2 joint mechanisms, one for flexion and another for extension. Both act simultaneously, and the upper part, right here, the cable is rolled up in clockwise direction, and in the lower part, the other cable is rolled up in the anti-clockwise direction. In this figure, we can see the mechanism. So the cable in upper part is the extension, and the lower part is for friction. Okay. As part of the mechanical structure design, is necessary to characterize the amount of degrees that the motor moves. The motor moves according to the cable length, the red line, so in the surface hand, and the total cable length difference. For this purpose, we know that the variable length are section long BP, long BM, and long BD, because they are a part of the cable above the joint and depend on the amount of the flexion in the fingers. In mathematical model, the layer figure illustrates the angles used to the kinematical model of the finger due to the movement it makes on the flexion path. From a bibliographic source, we took an angle of the finger joint while closing the hand around an object of radius rad. With these values, a polynomial interpolation was made which generated the relationship between theta1, theta1 in rad, so theta2 with rad is with theta1, and theta3 with theta1 again, to generate a movement that resembles the angular root during flexion just by assigning a value to theta1. And several simulation experiments.
1 minute.
Hello?
1 minute left.
Okay. Several simulation experiments were performed by modifying the radius of the objects to be grasped for the validation of the polynomial function as shown in the figure below. One for 40 millimeters, 30 millimeters, 15 millimeters, and 10 millimeters. The device was assigned a certain position to make an angle measurement. By taking continuous picture, the figure shows the comparison of measuring different positions respect to their simulation. And the difference between the measured and desired degrees generates a mean square error of 0.925. The efficiency of the device is 95% because the error is in acceptable control range. And finally, the differential mechanism for multiple fingers allows the glove to support with adaptive gripping movements thanks to the sliding movement of the cable through the U-tubes that allow a distributed tension for both fingers. Second, using a cable-driven mechanism provide reduction of factors such as weight and volume, so the glove is more comfortable compared to the hydraulic and pneumatic actuators. And finally, the radius of an object to be grasped is variable, so a function was obtained for the position of the middle and distal joint that depend on the flexion value of the proximal joint. Its effectiveness was verified with simulation and experiments. Thank you, everyone. Any questions?
Thank you, you're very kind for your very nice presentation.
Let me.
The time is very tight, so we don't have time for questions. But again, if there is anyone willing to make questions, can use the chat for this purpose. Maybe, John, only one remark. If you could show us a video, it would have been nice to see a video of your device.
Yes,
Do you have it?
Yes.
Okay, meanwhile, let me call for the next speaker, which is Magali Sganga, who is going to present improving the joint center location of the markerless motion analysis system through a functional calibration method, a pilot study. Sganga, are you there? Okay, the microphone is muted. So please unmute your mic.
Yes. Can you hear me okay?
Yes, we can hear you and we see something on the screen.
And you're watching the presentation, right?
Yes.
Okay, so thank you very much. Well, as Giuseppe said, I will be talking about improving the joint center location of a markerless motion analysis system through a functional calibration method, a pilot study. So my name is Magali Sganga. I'm working in Universidad Maimonides, Hospital Italiano and CONICET in Argentina. But this is a team effort, right? And the other participants were Marcos Núñez from FLENI, Lucas Ritaco from Hospital Italiano and CONICET, Marcos Crespo also from FLENI, and Emiliano Ravera from Universidad Nacional de Entre Ríos and CONICET. But what does it mean that if we are going to talk about improving the joint center location of a markerless motion analysis system through a functional calibration method, right? So first of all, we will be speaking about biomechanics, of course. Then we'll talk about functional calibration, Microsoft Kinect as one of markerless motion analysis system. This will be a topic of this presentation. And of course, we'll be talking about motion capture. So these will be the keywords of this presentation, and I hope I can transmit the message correctly. So as I said, we will be talking about biomechanics, how the body works, how the body moves, the force is acting in it. And inside the biomechanics, we'll be talking about the branch of it and its kinematics, where this body is in the space, the acceleration, the velocity. But to do that, we have to make some assumptions. What of those? Well, we need to know where the joint center is, just to know, I don't know, how much angle are we flexing the elbow or are we flexing the knee? Well, we need to know where the joint center is. And what is a joint center? Well, a joint center is a point which two segments move relative to one another. So we are talking about two different bone segments, rigid segments, and we need to know where this point is inside this joint. When we talk about the hip joint center location, it's really difficult to do that because it's really internal in the body. So we need to make a lot of assumptions just to know where this joint center is. So we will be working with two different technologies in motion capture. The first one is MoCap, and it's motion capture analysis system, right? So this is the gold standard, and it's great, it's super accurate, but we have a little bit of trouble. We have some troubles here, that it is expensive to have this laboratory working on motion analysis. It's time consuming because we have to implement the patient working on it. We have to put some marker in the patient's skin, and then it's not portable. So we cannot take the laboratory and to go outside or to go, I don't know, to a stair. It takes a lot of work to do this. So what can we do just to replace this? Well, we can use another technology, that is Kinect, Microsoft Kinect system. That it's a depth camera. Then, so it's easy of use, excellent. We need that. We want to do that. We want to have this. It's portable, so you can take the Kinect and just put it in a place, plug in, and it's working, and it's low cost. So excellent. But the disadvantages are that it has poor performances under certain circumstances, and then it's not accurate. So what we are trying to do, the purpose of this study or this work is to evaluate the feasibility of using skin marker techniques to compute the hip joint center location like OCST and SCORE in a markerless motion approach. So we want to take the techniques from MoCap to the Kinect system. So as I said before, it's a pilot study. So we had only one participant, one female participant. It was healthy. It has no motor impairment. And we put 4 pelvic and 4 thigh markers on the skin of this patient. So the method that we took is we put the patient inside the volume acquisition, right? Inside the acquisition volume. And we put the Kinect over here, and we had the cameras all around the MoCap cameras all around this volume. So we acquire a static acquisition first, and then we did 6 dynamic acquisition. We asked the patient to do a star plus an arc movement to determine how this hip is moving. In the methods, the mathematical methods that we use were OCST, that it's an optical common shape technique that was proposed by Taylor. And this is to minimize the soft tissue artifact produced by the skip movement, right? And then we applied a score technique that is a symmetrical center of rotation estimation that is to locate properly the center of the hip movement, rotation. So using this, we arrange or we minimize the soft tissue artifact, and using the other method, we work on the joint center location. So what is the data that we obtained from Kinect? We obtained a depth frame. That this means that for each pixel, we know at which distance the pixel is from the Kinect camera. Then we get the body index. This means that if the pixel is blue, this is a body. If it's green, it's not a body. So we discard it. And then we get a skeleton frame. That is, we know where is the location of 25 different joint centers. This is the raw data from Kinect. We didn't have to do anything, just plug in the Kinect. But how this work? The functional calibration with Kinect. So we take all of this input over here, and then we say, is this body, is this point a body pixel? Okay, we can take it. Is this pixel a part of a body? Yes, but does it belong to a type? Yes, then we can take it. So we get all of this, that is type points, okay, colored by green. And then we selected 5 random points, and then we created virtual markers reference to the NIP joint center. Once we did that, we get this output that is virtual markers, and then we can apply, the OCST and the score method just to relocate the hip joint center that we can see over here. That is the raw data, and then we worked over this raw data just to relocate the hip joint center. So the results of this study is, for mocap plus functional calibration, we get over here we can see mocap and functional calibration, and over here in the y-axis we can see the x coordinate of the hip joint center in meters, the y coordinate, and the z coordinate. So we know where this hip joint center is in the space. So this is for the gold standard, as we said before. We can see it over here. So as we want is the Kinect to locate the hip joint center near these values, right? But we discovered that Kinect, it's not quite accurate. That is something that we already know before. So we have the Kinect results over here. What we want to do is to take this raw Kinect data and process it, and then obtain a value that is nearest this value, right? The gold standard. And the results we get is that, hey, we did it. We improved the location of the hip joint center. That is an excellent view. So we, in the X coordinate, hey, we did it really good. Y coordinate also, we did it excellent. It's just like 10 centimeters, the correction, but we didn't get such a good result in the Z coordinates because we're talking about the depth camera. That it's okay, it's probably that we didn't improve this amount of location of distance that much. But as we interpret this position is that, okay, we get less variable. The results of this, because we get an average, it's less variable, as you can see from the box plot. So we're really happy about this, and we think this is a feasible study just to keep working on. It's a good line to keep working on this. So what are the conclusions? And I will be closing up for this. Okay, we had a pilot study. We applied functional calibration to Kinect data. That is something new. We didn't find this in the literature. We obtained an improvement of the hip joint center location. So we can say that this is a feasible method to be applied from Kinect data, because it doesn't take a lot of time, and we can correct the data from just to make sure that the calculations of angles and velocity that we are making are greater and are more accurate. So we are really happy about this, and this is the line we are working on right now. We already present the next step for applying this to a lot of people, and we are the work is in the ethics committee. So thank you very much. Is there any questions?
Thank you, Sganga, for your very nice presentation. The paper is now open for discussion. Is there any question from the audience? Okay, if not, I have a small question. You mentioned about the accuracy. Did you check if after the calibration, this, let's say, performance is replicable? So you keep again and again the same result, or just there is any need of further calibrations afterwards?
Sorry, I didn't understand the question. We did this with one person only, and the results we get were this one. So right now we're waiting after the committee of ethics. It says okay, and then we can just.
No, I understood this point. The question is, with one single patient, how many times you did this thing?
We did this. We took 6 dynamic acquisition, and we did that once.
So just one time?
Yes.
Okay, I understand. Good.
We calculate the average of all this acquisition, and then that is what we showed.
Yeah, my question was, if you do it again and again, you get always the same result, or something is changing?
We didn't try that one. I will take note for the next study.
Okay, thank you very much.
No, thank you.
Let's go to the last presentation, which is by myself this time. So I will turn on my screen, and okay, just confirm you can see my screen.
Yes, we can.
Okay, thank you. Good. This work today regards force control architecture for grasping with a robotic finger. This work is mainly a student work done by Bart Padron, who visited our University of Calabria in Italy for a bilateral exchange program. So he was intended to present today, but suddenly he disappeared. So we, on the rush, prepared for this presentation. I apologize for this. So in our team, we have been working on grasping and robotic hands for something like 20 years, developing several prototypes, as have been shown in this slide. So the idea here is to design a low-cost version of this robotic hand, especially one finger of such robotic hand, and attempting to improve its control architecture, basically by integrating position control and torque control. So here is the main concept of driving mechanism for such a finger, where we have only one active degree of freedom, which is able to bend the 3 phalanxes, as you can see from this slide. So the yellow axle is rotating, and following this, the 3 phalanxes move in a human-like behavior. Here you can see a detail of the driving mechanism. So the original driving mechanism of Larmand is reported in table 1, with main link lengths of the driving mechanism reported here in millimeters. Also, some adjustments have been done on the link lengths to obtain a more compact design in the presented version. So here you can see how it looks like. It's very simple, it's 3D printed, and can be easily operated. So the idea is to combine, as I mentioned, the position control and the torque control via current sensor. And our concept is to avoid in this way the use of force sensor. So we would like to estimate the force by using a proper kinematic and dynamic model. And so based on position and torque, we can estimate what is the contact force on the interface with the object. Here are some basic equations, mostly closure kinematic equations, and basic dynamic model has been made using a simple Lagrange approach. So here you can see some pictures of the finger and where we depict the positions of the main bars of the actuating mechanism at 3 different configurations. So here you can see also a detail of the finger while grasping a soft object. So touching rather than grasping, actually touching a soft object. And you can see some of the calibration parameters. In particular, we calibrated the force using a force sensor. We have been able to estimate how much force is obtained at the contact surface and relate it with the input torque that can be directly measured via a current sensor. So here are some plots of the obtained results, both in terms of angular positions of the input actuator, and some details on the, in figure 6, some details on the finger force. So what we obtained as finger grasping force and what we have as input are shown together in figure 6. So in conclusion, what we have here is an attempt to have a simple force control architecture which integrates both kinematics and dynamics to estimate the contact force as based on direct measurement of the angular input position and on the input motor torque. Preliminary experimental tests have been done, and from there we obtained the confidence, estimation confidence on the contact force of about 85%. Still further efforts are needed in terms of testing to more carefully model friction and backlash, which contribute to the overall estimation accuracy. So that's all for my presentation. I open now the paper for discussion. So if there is any question, feel free to ask. Of course, I cannot do questions to myself. So, Martin, I leave this in your hands.
Giuseppe, I have a question.
Yes, Juan Antonio, please.
Yes, so how different is, so you put in the diagram, one of the diagrams that you had there, or the animation, that this is a patented mechanism. I just want to know how different this is from other under-actuated fingers, like the one that at Université Laval they have been using for years.
Yeah, this is not under-actuated at all. This is based on cross 4-bar linkages. So I don't know if I can.
I didn't get that. Sorry. This. So I guess I got distracted.
So they are cross 4-bar.
That means linkages. The motion is correct. So the
kinematically
motion. Okay.
It's one active degree of freedom, no under-actuation. So we can move only in one possible way, no under-actuation.
I'll show you really again. Grasp.
Only
means that you cannot really
cylindrical
grasp.
objects, only cylindrical objects
Okay.
of the predefined radius. So it's not for everything. Cannot adapt to the shape of different objects.
Okay, understood. Thank you. I missed that.
You are
That's a very
welcome.
important point. Yeah.
Yes, yes, that's a key point actually. So you grabbed exactly the most important thing. Thank you for asking. Okay, I think we are mostly on time. So I switch off my video and I just would like to thank all the attendees and presenters for this very nice session. And of course, I would also like to thank the organizers for this very tough work being here to attend all the sessions. It's really a pity we cannot meet in person, but I really hope this will happen very soon in next occasion. So thank you very much again, and let's clap hands to Martin, Giuseppe,
Thank you, Giuseppe.
and the organizer and participants.
Thank you very much
thank
for chairing the session. Thank you to you.
You are very welcome.
Thank you, Magali, Oswaldo, and John. A bit accidentally, but nice presentation, very complete. And thank you for cooperating with Latin American people, Giuseppe. Thank you very much.
You are very welcome.
So,
thank you.
I want to announce that the proceedings are pre-published. They will be available in 2 weeks, but now, if you wish to see it, I will copy in the chat. This is the pre-published. Once they send me, I will send the book in electronic form as soon as they are available. Maybe in 2 weeks. Tomorrow we will have a plenary speaker by a plenary chat by Jorge Ambrosio, and then a regular chat. All the talks are confirmed, all the talks, and then there will be a ceremony, closing ceremony with the awards. Please be present, be there. It will be a closing ceremony. Thank you very much.
Thank you very much. We will meet tomorrow then. Bye.
Good night, Giuseppe. Good night to you. Good evening, the remain.
Thank you very much.
Tomorrow.
Bye-bye.
Bye-bye.